Okay, tonight's speaker is Dr. Scott Schneider from the Lawrence Technological University. He's been teaching physics there since straight out of grad school and since 1992.
Usually said that's not even knowing so, but
very clearly said 1992 is what he's told me. Anyway, they've had an Astronomy 101 course there for about 10 years, I guess, and it reignited his interest in amateur astronomy, and he bought himself a fancy telescope, maybe about, what, a year ago now?
yeah, that's fun.
And he's still continuing to accept responsibility and blame for cloudy skies, so we need to snatch that away from him.
I went up to the Adirondacks, upstate New York, and mostly clouded out the nights out there. So.
Okay.
So you can totally blame me for last week.
Pretty impressive, yeah.
Okay. Anyway,
Thanks, Bob.
He dives right into the things most of us avoid, astronomical calculations, either writing code or using web resources, what he likes to do. He's gravitated towards making oddball calculations, some of which fit the Mount Everest reasoning paraphrased as, why calculate that? Because we can. Turn that over to Scott.
Okay, thank you.
Hey, proud with us.
So I'm doing audio recording. Audio recording here, so I'll do a snap so you can figure out to sync up the audio with the video. So you'll have to account for the difference in speed of sound versus speed of light. Okay, so some of this is, there were some great questions at the end of the last talk. I gave sometime in April, I think. And so I wanted to do some follow-up. And my sister-in-law, Mary, was kind enough to write down the various answers. So the ones that I could pick and choose and cherry pick and say, I think I can calculate that, I pulled a few of those in, and I got a few other pieces in here. So let's take a look. We had that Venus-Earth Mandela sort of figure. This was out on the internet, and I think this is the one from the internet that showed the five-fold symmetry. And if we plotted a line between Venus and the Earth and just drew a line, and then stepped it through like every week or every month or so forth, we get this five-fold symmetry. So it was 8 orbits of Earth and 13 orbits of Venus. So 13 minus 8, I can do that. 5. Oh, five-fold, is that going to be that simple? So we were playing around with that, and then the question came, well, what if you had other planets? What if you had other, because I plotted out, here's what Earth and Venus actually are based on their locations. And yeah, it does come out, so the internet, in this case, was correct. But then the question was, well, what if there are different ratios? What if there were different orbit numbers around? So I started playing around with that and decided that it's when there's superior conjunctions, when on the other side of the sun, the thing in the middle, that's where the two planets are, that's when you're getting these spots where a collection of the lines. So all the lines are all collected on top of each other. So, but let's play around with, well, how many superior conjunctions would you have depending on what ratio of how many orbits from one planet and how many orbits from the other. Turns out it's take the difference in the orbit times divided by, of course, the greatest common multiple. That was obvious for everybody, right? The greatest common multiple is what we want to find there. So let's play around with this. This is one. Can we take the lights down just part way? Or
this is as far down as they go.
All or nothing? Okay.
No, don't turn off all of them, please.
Well, just for this one slide, maybe. So here are the two planets here, and I think I've got a 3-to-1 ratio. So one's going to go around 1 year, and this takes 3 years to go around. So they line up here, and then one of the planets come all the way around 3/4 of the way around their orbit, whereas the first planet only gets to 1/4 of the way. But you can see that they're opposite the sun now, and as this thing's whipping around here, that's where we're getting these lines to collect. Okay, so I've got a little program that'll let us map that out and show those. And so now this one, so if I do 8 and 13, here we can calculate the 8 and 13 and have those go around. This will give us that five-fold symmetry. So it's just plotting, here's the outside planet, there's the inside planet, draw the lines between them. And it goes around, and I've got it set for 1,000 times. But there's that five-fold symmetry in there. Okay, so now let's go back to that 1 and 3. I've got to finish. So 1 and 3.
Wow.
Okay, 0. So 10. So let's go calculate stuff. Okay, here's the 1 and 3. So 3 minus 1 is 2. There's our 2 times where we get these superior conjunctions happening around that in that orbit sort of path. So this gives us the 2-fold pattern, the 2-fold symmetry. I think oh no, that's right, that's good. Okay. Wait, let me go one more step there. That's fine. Okay. So now, back to this. So what if I did 2 and 3? So 2 and 3 is going to give us how many? 1. Right, there's our one-fold sort of symmetry in it. Because 3 minus 2 is 1. Okay? What if we did 4 and 2? So 4 and 2 is going to give us, of course, 1. What the? Okay, 4 minus 2 is 2. I can do that. But if you think of it as 4 minus 2, or 4 and 2, it's really 1 and 2. Right? 4 divided by 2, 2 divided by 2, it's really a 1 to 2 ratio. Well, 1 to 2 ratio would give you that one-fold symmetry. So there's that greatest common multiple between them. The greatest common multiple is 2. 2 times 1 or 2 times 2, greatest common multiple would be 2. So take the difference, 2, divide by that greatest common multiple, 2, gives us the 1. So we should be able to predict any of these numbers based on whatever the cycle. So what if I did 5 and 2? Neither have a common multiple, right? So it's going to be 5 minus 2, that's going to give us 3. So here's our threefold symmetry. 1, 2, 3. Okay. So if we go to 2 and 6, that's 4 in between, but there's a common multiple. 2 is a common multiple. So if I said, well, 2 divided by 1, 2 and 6 divided by 2, I'm 3 to 1. Well, 3 to 1 is a twofold. So 7 and 2, now we're up to fivefold.
That's an 8 and 2.
That is an 8 to 2, of course. So what I meant was that's a threefold, because 8 and 2, the difference there is 6, but common multiple of 2. So 6 divided by 2 is 3. So that gives us threefold. So what did I want? I wanted 7. Well, let's go. Oh, let's try another one. So what about a half integer? So what if I add a half integer? So if you look in this box here, this is 2 to 8. So I'm going to add a half integer. I think I added on the second one, on the 8. So if we put a half integer, but let's drop down our second cycle. Let's make this 2 and 3, but really it's 2 and 3.5. So 2 and 3.5, what we have to do is we have to double it. We need integers. So if I double them, it's really 4 to 7. Well, 4 to 7's got no common multiple, so 7 minus 4 is 3. There's our threefold symmetry. What happens if we're not on integers? What if we don't have a 3 to 4 or 5 to 7, whatever? What if we go irrational? So I can add a little irrational piece, and then we say, okay, so this is now 2 to 3. Why did it do? Oh, you know what? I think it overrode by saying half integer. So we take off half integer. Okay, so this is now 2 to 3.3 something. So that doesn't, whoops, wait, that's not, is that 1? No, 2? No, wait. 3? No, that's 4. No, wait. Irrational, we're not going to get it to match up. Right? If we don't get it to match up, it's just going to start filling in. It's got no spot where here's a superior conjunction, there's a superior conjunction, that's it. You get 2 around there or 3 around there or whatever. So it'll just fill in all kinds of mishmash. If we left the Earth and Venus to go, the real Earth and Venus, we wouldn't see the fivefold symmetry anymore. Because it's not truly 8 and 13. It's 8 and some change, 13 and some change. They're not going to match up really easily over a long period of time. Okay. So that was playing around with what happens if it's this, that, or the other. So there's the differences. If it's half integer, we do that. If it's irrational, overlaps. Okay, so there was my program. Okay, the shadow line on Venus. I believe if I got the note right, the shadow line on Venus. So actually, we could leave the lights off just for a second. I'm going to get my sister-in-law. So Mary was the great scribe last time to help us with recording the questions. And she was mad at me for surprising her with, Mary, quick, come up here. You got to do this with me. So this time I gave her all the advance notice of an hour and a half to tell her, I'm going to use you again. So, okay, so you're the sun, right? You got your flashlight. I told her you get to shine a light in my face. So, here, come over here for a second. Stand right on the edge of the light so you're out of the light. Right there. Okay. So you're the sun, shine here. Okay, so I'm Venus. Venus is going to go around the sun. So let's say, because the question was, can you walk faster, assuming you had a spacesuit, can you walk faster than the terminator line, the shadow line that's moving around Venus, let's say the equator around Venus. So as Venus rotates on its axis and has it orbits, can you walk faster than the terminator line? So here's the sun on me. So let's pretend I'm only going to orbit the sun. I'm not going to turn on my own axis. So here's the shadow line. So here's a shadow, right? Here's a shadow over here. So if I don't rotate on my axis, and I only go around the sun, I'm going around the sun this way, what's the shadow line doing? It started here. Where's the shadow line turning to? So you turn and fix me. Yep, okay. The shadow line's moving to here, right? This half is lit up and this half is not lit up. So here's the shadow line. The shadow line's back here. The shadow line is moving that way around. So looking down from the top, it's going counterclockwise, right? So looking down from the top, here's the shadow line. The shadow line's moving around like that. So from the perspective of Venus, it's going counterclockwise. Remember that direction. Okay. But Venus rotates on its axis. So there's going to be another effect that with the shadow line, because if I just stood here and rotated, now do I rotate like this? Up, up. Okay, go the other way. So remember, Venus is retrograde. It rotates, we all go around that way, and we all rotate on our axis that way, except for Venus rotates the other way. So I'm going to stay here and not move around the orbit, but what if I rotated? So here's the shadows. What if I rotated on my axis this way? So the shadow line is here, the shadow line's here, it's also going counterclockwise, right? So the effect of me going around the sun, counterclockwise shadow, the effect of me rotating, which way? Clockwise, on the axis is the same thing. It's still going counterclockwise on Venus. So both of those effects have to add. It'd be better if Venus rotated the other way, because then they would start to cancel out because they're really close to each other. But they add up, that's going to cause us problems. Okay, thank you. Okay, keep the light out of my eyes. Come on. It's not what we discussed.
What is Venus? It's 243 days retrograde?
Right. So let's look at, so here's our numbers. It's the same chart I had last time. And we've got Venus here. Where's our Venus? So 224, that's the orbit period. And then on its axis, so sidereal with outside stars, here's the 243, and it's got a negative because it's going the retrograde. Everybody else is going positive. You always have to look at Earth to line up. Yeah, number of days in the year, got it. 1 day on the axis, got it. Okay. So these are the numbers we care about. We were looking at Mercury last time. We don't care about Mercury. So these are the numbers, and basically Venus is very circular-ish. If you look at all these planets, this is the most circular out of all the eccentricities in our planets. So let's give me 1.6. Let me do an average of the rates of the going around the sun part, and then here's the rate of going around the axis. But what we know now is we've got to add those two rates. So that being angular, that's going to be how many degrees per day does that shadow line move. But we have to add up the two numbers because they're both going in the same direction. Okay, so we care about only Venus. We're going to look at that 1.48. We're going to look at the 1.6. Man, if we could take the difference, that's a small degree per day. That might be walking speed. But we have to add it. So, I don't know why I keep walking over here because I've got my clicker. Okay, so there's the two numbers. Shadow line moves that, shadow line moves that, but both of them go in the same direction, that same counterclockwise, so we have to add them up. Okay, we got roughly 3.08 degrees per day. At the equator, circumference, there's our radius, there's our 2 pi, so 38 and some change kilometers, 38,000 kilometers. Or we could look at it this way. If I do 3.8 degrees per day, and again, I'm using Earth days, I'm not using Venus days, because we're the ones doing the calculations, so we're going to go Earth. If I go 308 degrees out of the 360, I can see how much of the circumference do I have to walk in that one day. So this divided by this gives me a small number. That times the circumference is going to give me 325 kilometers. So in my one day, I'd have to walk at a rate, so I could cover 325 kilometers in a day. Now, I don't know about that. So we do that conversion, meters per second, 8 miles an hour. I'm not walking speed at 8 miles an hour. So walking speed's about 3 miles per hour. But if you think about it, Jonathan.
Can we turn the light on?
Oh, yes. So because you can't see me. Like, if I stand here, you can see me on the camera. So 8 miles an hour is a little too fast for walking speed. 3 miles an hour, you could do it. But if you think about it, these bodies are fixed. We're not walking on the sun, because that's got a variable rotation. But any fixed body has the same angular velocity. But how fast it goes around the axis depends on what latitude you are. Right? You've only got a small distance to go around near the North Pole. you got a much bigger distance to go around the equator all in the same amount of time. For that, at least that's rotating, that shadow line is rotating. So you could walk any terminator line. You just have to pick the right latitude. So if we go for Venus, we've got to go for cosine of the latitude, so 0 degrees here, that's going to give us the full time around. There's no way we're going to do that. That's 8 miles per hour. I should have switched this over to kilometers per second for a science talk, but 67 degrees latitude. If we go 67 degrees north latitude on Venus, you could outwalk the Terminator. Anything higher than that, piece of cake. Because the North Pole, I can go, boop, 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 walk around the North Pole, I'm way faster than the Terminator there. But you got to be at least 67 degrees north latitude for Venus. So of course I said, well, okay, that's Venus. Well, what about the Earth? So the Earth is, here's the equator, there's 360 degrees per day. We're whipping around our axis compared to Venus. This is not going to work. So now we're looking at 1,033 miles per hour at the equator. Yeah, I'm having trouble flying that, let alone driving that, or let alone walking that. So we got to get up to 89.83 for walking. So so here this would get you the Venus speed of 8 miles per hour. But you got to get to 89.83. So you're basically boop, boop, boop around the North Pole to be able to get fast enough to watch that Terminator line, to be able to outstrip the Terminator line. That's not really going to work. What about the moon? Now, if you're not sick of me after 2 sessions of astronomy talks, I do have something about the moon, because we can make the argument that the moon orbits the sun, not the Earth. And looking at its path through space, if you imagine, so imagine right now, close your eyes and imagine, what do you think if we could step out north of the solar system and look down on the moon's path, are you picturing a curlicue loop-de-loop-de-loop as it goes around? Because it's going closer to the sun, away from the sun, it's orbiting the Earth, so it's going to go loop-de-loop-de-loop. The moon actually never curves inward. Never curves outward. It never does a loop and curve outward and come in. The moon only curves inward in its path around the sun. It curves inward more, curves inward less. So there's another talk. If you're not sick of me after 2, I've got a 3rd one lined up. Okay, so the shadow rotation. So right now, let's just look at the axis rotation of the moon. Don't worry about its motion around the sun, because that's only going to help us, because it's rotating the right way, and it's going around the sun the right way. So, but that's 13 degrees per day, circumference, blah, 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 21 miles per hour. Okay, so we only have to be 81 degrees north to be able to do this on the moon. Okay. So then, I thought about if the sun can stop in the sky at Mercury, right? Because remember, Mercury's got the 2 rates that are opposing each other, which all these other ones are too, but we have one rate that's way too fast. But Mercury's got 2 rates that are close and they're opposing each other, so you definitely could do it on Mercury. Because we can get Mercury, we can get the sun to rise, stop, and go back and come back again. Or even just come up and pause and then keep going. So you could easily walk the Terminator line on Mercury. So going back to the Mercury talk that I gave, that would be the time to say, hey, I think you can walk faster than the Terminator line on Mercury. So any other planet farther out, we're going to have trouble. But Mercury, we could actually do it under the right circumstances. Okay, so length of the seasons. Does any of the parents in the audience or grandparents are going, when do the kids go back to school? Isn't the summer over with yet? Can't we get them back into school right now? So the question is, how long are the seasons? We have 4 seasons a year. We've got the certain dates of when we say astronomically, here's when the new season starts. And they're roughly 90 and some change, right? 89, 90 days in between, from start of summer to end of summer, start of, what's next? Fall, end of fall, and so forth. Okay, so calendar stuff. We talked a little bit about this last time. The seasons were drifting around, so they had to restructure the calendar. So the Julian calendar had a leap day every 4 years, but that wasn't going to work. By the 1500s, they could see that was slipping, and you'll see a graph for this. We've got this pesky 365, 24, 219 days in the tropical year, so it doesn't divide up nicely. So if we do the Gregorian, we say, okay, every 4 years, great, but every 100 years, wait, don't do it. But every 400 years, yeah, do it. And we're going to need another change later on. Maybe a 4,000, maybe a 3,600. We played around with that last time. So let's take a look at leap days. But the problem is the Earth's orbit's drifting as it goes around. It's precessing. Because of all the pull from the other planets and the pull from the moon, our orbit's precessing slightly. Well, that's going to affect how close or how far the the close part and the close point and the far point, aphelion, perihelion, where are they located in our space orientation? So we've got our angle where we say, let's point out here the point of Aries. Let's start our 0 degree and go around like that, and then go angle up. So we've aligned ourselves with a space, what do I want to say here? Coordinate system, a space coordinate system. Okay. The problem is the orbit is slowly rotating, slowly precessing. So let's see what that does. Okay. So we have all the planets go around the sun, same direction. Okay, ecliptic, got it. Earth is sometimes closer, sometimes farther. So there's 2 points in the orbit we can point to and say, here where we're closer, here's where we're farther. So I plot out the graph. This isn't where the planets are today. This was, I think I gave this back in, I gave it 10 years ago, so 2006. And so I think that's the date that I gave it was somewhere back here. Yeah, 2006 is when I gave it. Just by comparison, we can see March 20th was the moment of spring, the day of spring, or the 19th. June 21st, June 20th, September, they're shifting slightly. They shift a little bit. It's not the same moment in time every year. But here's our perihelion close. Here's our aphelion far away. Notice aphelion's in the summer, and that little school kids go, wait, when are we cold? Oh, cold, we must be far away from the sun. No, it's the tilt. We all know it's that pesky 23.5 degrees tilt. Okay, but if we're out here farther, we're slower. If we're in here and we're closer, we're faster. We're moving faster in our orbit. So we whip through, and here's where we line up our fall and our spring and our winter and our summer. I can get 3 out of the 4 seasons. I can't remember the last season. Here's where we line up the spring, and that goes by, here's our tilt, and we've got our equator that goes out, and then we've got our plane, and sometimes those 2 planes meet in a line, right, the floor and the wall. And where that line passes through the sun, that's where we line up the spring equinoxes, right? Here's our solstices, here's our equinoxes. Okay, so those 4 points stick, and they're 90 degrees, 90 degrees, 90 degrees. But we spend more time out here. We spend less time in there. So winter and whatever the other one is, spring, we have less time that we spend in there. Slightly fewer days, slightly more days here. So the summer's a little bit longer, and the fall's a little bit longer, and then winter and spring are a little bit shorter. The problem is, this whole thing is rotating. So the close and the far are rotating around. That's going to change who gets to be longer, who gets to be shorter. Okay, let's go back and look at our calendar, or let's do this. So here's a great little time for the seasons. When is the exact season? So if you look at this column here, here's spring. I just picked one of the cardinal points to look at. But here's spring. So March 20th, all the same, okay, and it's a 10-year span. So, but then it's 23, UTC, 5, 11, 16, 22, I don't see any rhyme or reason to these times, right? The time during the day when that moment of spring is. Well, anytime we get numbers like this, what do? Got to graph it. Got to see what it looks like on a graph. Ah, this makes a little bit more sense on a graph. We got 2011, 2021. So what happens in 2012? What happens 2016? What happens 2020? We've got a dropping here, and then we do something. We've got a jump. We come up to here. We've got another jump. Come up. What's the jumps? That's the leap days, right? We're starting to drift. We're drifting too far up like this. Wait, let's drop us back. Drifting too far up, let's drop us back, and so forth. But do you see a trend in that graph, the overall graph? So forget the hops every 4 years. What's the other trend? It's dropping, right? Every 4 years isn't going to cut it. So we go to the next one and say, first of all, here's that Gregorian Reformation. Their moment of spring was the 16th, the 14th, the 12th. They could see this thing was getting way out of whack. So they said, hold on, let's bring it up to here. Let's put spring back where we want spring to get the fall equinox where we wanted it. And let's do our every 4 years, every 4 years. But now you can see over a long period of time, this is 16, 18, 2000. What are the jumps at 18, 2000? Those are the 100-year jumps. Or wait, 18, 19, 2000, and so forth. So those are the 100-year jumps. But now you can see another trend. The other trend says, whoa, too big. Okay, wait. So let's skip some. 2000, skip it. At 2400, that's over here. 2400, skip it. At 2800, skip it. Okay, so great. Now we've got it up, too high. Okay, wait, drop down, great. Up, too high, up, drop down. But now look at the graph. What's the overall trend now? Dropping again, right? That's where we're going to have this. Oh, remember this? Every 400, every 400, don't do it. Every 400, don't. Wait. 4 do it, 100 don't do it, 4 do it. We're going to want a, no, don't do it. Maybe 4,000, maybe 3,600, whatever you want for that. Okay. But we can see that overall trend of the downward drop like that. Let's take a look at averaging out all those little bumps. Let me go past this. Let's average out all the bumps. So we're looking at now, I got 1,000 to 3,000. So here I'm plotting out winter, spring, summer, fall, the number of days of that season, counting between when the spring equinox is to the solstice, solstice to the equinox, and so forth around. So we get roughly 90 days, right? 4 times 90 is 360, 365, so go a little bit more than 90. Here's just around 90, adds up to 365, 0.25, whatever. But if we look at where we were, remember we were back here with our spring. Over the course of 10 years, spring seemed to be shifting earlier, slightly. On that particular date, here's the 21st, somewhere on the 20th, we're shifting earlier and earlier in time on the 20th. So if we look at this pattern, whoops, this pattern, so we're here near 2000, so a little bit over, here's our spring dropping off. Our spring is shifting down just slightly. Winter is, or summer is growing, right? Summer's going to get up to 94 days or so, its share of that orbit. Depending on how we process around, that's shifting summer bigger, shifting spring smaller, and here's the two, winter and fall, are the lower ones, but look at fall. Fall's rising. Let's go even wider. So here is now a nice 10,000 year span. All I'm doing is looking at the precessing of the orbit. That's all we're looking at, is precessing of the orbit and then counting up how many days we're going to have between those. So winter was really huge back here, right? Winter was a long time, long relatively, 93 days. And spring was right around the same time, winter and spring. We're heading into, so winter is coming, but winter is not really going to be coming until year 4,000 or so. Then we can see winter's coming back again. So, well, Game of Thrones here. So, the problem is what's missing in this? What am I not taking into account? I said, oh, okay, here's where we count the cardinal locations. There's our equinoxes, there's our solstices, based on how the orbit, how the axis of the Earth is tilted, how that equator line goes out, how it lines up with the ecliptic, the Sun-Earth plane, where that line goes in space. So I said, all we're going to do is watch that orbit process around. What am I missing though? If I'm on this small scale like this scale I'm comfortable with. This scale, I'm missing something.
Because the line of the Apsides is changing.
There we go. So we are pointing at the North Star right now, very conveniently, but around 26,000 years it takes us to go around, spin like a top, and come back to that spot. So 13,000 years, we're pointing somewhere else in the sky. Well, if we point somewhere else in the sky, that just shifted where our summer, winter, spring, fall, where the equinoxes are, where the solstices are. So that's going to screw up this graph, certainly on this scale. This scale, I could probably get away with it. But on this scale, I'm not dealing with the Earth being a top. This is now a 10,000 year scale, 13,000 years, and this Earth is pointing, the North Pole axis is pointing to another place.
Vega.
What's that? Vega, right, it's going to be pointing around. That's too hard a calculation, so I didn't even think to try and do that. Maybe I can come back for version 3 and play around with that, but no, it's not. But then to add it on to the other one, and I just didn't.
Yeah, to make those coincide. Oh God.
It's going to be complicated, right? Okay, so Earth is a precessing top. There's the 26,000 years. It's going to come back around roughly 26,000 years. So in the short run, I think I'm okay. 10,000 year graph, maybe a little bit off. Okay. Planetary alignments. So this is one where if you follow the Tomb Raider series, the second Tomb Raider series, second Tomb Raider movie, had all the planets lined up in space, in a line, like one after another, like pool balls. Boom, 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 right down the line.
Is this some recent film?
No, this is an ancient film. Ancient by modern standards. So this is probably, what, mid-90s?
Could you give me a spelling on this? Tomb Raider?
Tomb Raider. T-O-M-B. Raider. Yeah, it's right down here. So Lara Croft Tomb Raider. Came from a video game, and they made a movie. Angelina Jolie. Wasn't in your wheelhouse, I'm not expecting it to be.
Not in
So
his wheelhouse.
I'm just going to point out how wrong they were, so you'll appreciate
He's
it.
not even watching.
Absolutely, yes.
Right, okay.
Just urinate on
It's in the moving pictures that show up in, it's in the moving pictures. Okay, so the lineup in space, the alignment. So can we have, and I just had somebody, I was out with a telescope and somebody said, oh, there's a big alignment. No, there's not a big freaking alignment. So the question is, could we ever have the planets line up all in one line? Well, we're going to approach it a couple different ways. It basically can't happen because the orbit tilts are going to throw us off. They're not going to be in a single line anyways, because all the orbits are in different spots and we can't get them all to be in the same line in space at the same time. What if they were all flat? So let's play the what if game, right? What if they were all flat? What if we could line them up initially? Maybe we could ask the question, when would they line up again? Because we can do hot dogs and hot dog buns and make this argument. So, hot dogs come in 6-packs, hot dog buns come in 8-packs. They don't line up, right? So we're going to play with all these different planets with the different periods, the different number of times they have to go around the sun to line up again. So let's play around with hot dogs and hot dog buns. I buy a packet of 6 hot dogs and 8 buns. I got 2 buns left over. So I've got to buy now another packet of dogs. Now I've got 4 dogs left over. Well, now I've got to buy a packet of buns. Another packet of buns, 4 buns left over. Another dogs, 2 dogs left over. Another buns, 6 buns left over. Oh, good. Packet of dogs, I'm back in sync again. I just lined them up again. I needed 4 packages of hot dogs and 3 packages of buns. I got 24 hot dogs, 24 buns, I'm done. I'm sick of hot dogs at this point because it's been 24 hot dogs later. But that's the cycles where they line up. So here is the time I have to wait 24 meals to get them to line up again. Those 2 things. Now we're going to put a bunch of planets together and try and get them all to line up again. So let's play around with synodic periods. This is when something lines up again with the Earth. So when we talk about the moon lines up, so the full moon to full moon time is different from the moon orbits the Earth time, right? Because the moon's going to orbit and go around according to the stars, but then it's got to go a little bit more to line up again, to be full, to be opposite the sun. Okay, so synodic. If I had 1 year for planet 1, 2 years to orbit for planet 2, how many years for planet 3? Well, 3, just to make it easy. So 3 years, how long do I have to wait to get them to line up? 6 years, right? I've got to let them go around. This has to go around twice, this goes around 3 times, that goes around 6 times. That would get them all to line up properly. So I'm looking at, now we're playing least common multiple. Instead of greatest common multiple, we're playing least common multiple. All this freaking math in the solar system, I don't know, what's the deal? So, what if it's 1, 3, and 4? Now we've got to go to 12. Do least common multiple for those 3 numbers, it's 12. What if we have 1, 4, and 6? Well, it's still 12. And the way we do this is we look at what are the factors with the highest powers. So 4 is 2 squared, so that's the power of 2 is squared here. 6 is a 2 to the power of 1 times a 2 to the power of 3. Okay, well, this is a factor with a power, that's the highest power, 3. This is 4, 2 is the highest power, 2 is the highest power. This one we ignore. 1 is 1 times 1, it's easy. But so I'm going to do 2 squared times 3, 2 squared times 3, 12. So that's how you do least common multiple. If we add more precision in these, I just did 1, 4, and 6, that's pretty easy. We have no planets with 1, 4, and 6. If we add more precision, this is going to get bigger and bigger. So one way to do it is to set it up, whoops, come back. So set it up with, let's pick our planets and let's round off our periods. So if we look at synodic periods through the Earth, these don't look normal, except the other ones sort of look like the period of the Earth going around the sun. But these are synodic. This is how long does it take for Mercury to line up with us? How long does it take Venus to line up with us? Jupiter to line up with us and everything. Notice we basically have a spike right near Earth, where if we had a planet just a little bit out from Earth, we're going around faster, they're going slower. It's going to take a long time for us to go around and lap them again. It'll be a big, long time. If they were a little bit in, same thing, big, long time. So there's actually a spike right here where it spikes up, comes back down. Spikes up, comes back down. The later planets are easy. Neptune essentially sits there. We go around the sun a little bit longer than 365 days, and boom, we're lined up with Neptune again. So Neptune now, whenever Neptune's at the zenith in our sky, basically a year later, it's going to be right there again, right? The other ones get all crazy. Where's Mercury? Where's Venus? I can look at the books. But Neptune's like, yeah, Neptune. Okay, it's there. Next year, it's there. Same time. So, synodic periods. Well, let's round these off. Let's just go one significant digit. Let's just round off to 100, to 600, to 800, and so forth. Let's add these up. Here are now my planets. Now, what I've got is 4 planets in the same orbit, because they're all rounding to 400. If I look for that, what I've got to do is look for all those prime factors. Here's all the 2 to the power of this, times 2 to the power of this, times 2 to the power of whatever. Now, keep only the highest powers from all those pieces. So keep the highest powers. Whoops, come back. Keep the highest powers. Okay. Calculate the least common multiple. So I need 2,400 days to align again. So basically 7 years. If I only had these 4 planets at that ratio, so 1, 6, 8, 4, we're looking at 24. Right? Take off the 100. Not bad. So 7 years they line up again. Okay, because these are all days. The periods are done in days. Okay. Well, let's go to 2 digits. What if I go 2? Well, now I've got, all those are now different. Well, no, 370 and 370. I've got 2 that are the same. Well, let's do the same thing. Prime factors, keep the highest, least common multiple. Okay, so now we're up to 8,000, or 87, wait, how do you say that? 870,000 years for just at this resolution to line up these planets. And I'm only doing out to Neptune. Okay, well, let's go to 3. So 3, and we say, let's find the prime factors. Let's keep the highest, let's least common multiple. Ooh, 10 times the current age of the universe. That's not good. And I've only gotten to, I've just barely gotten these resolved relative to each other. Well, let's go to 4. So if we go to, so prime factors, keep the highest, calculate number of days to alignment, 10 billion times the age of the universe. It's not looking good. But, hang on a second, let's go to 5. Remember this, 10 billion times the age of the universe. The previous one was what?
10 times the age of the universe? It was just 10 times the age of the universe.
So 10 times the age of the universe, okay, we jumped to 10 billion. By jumping to 4, we jumped to 10 billion. Okay? Now, jump to 5. 5, prime factors, keep. Whoops, least common multiple. 705 billion. We went from 10 times to 10 billion to only 700 billion. Maybe there's a sweet spot out there. In terms of resolution, how far we do the resolution of the, but wait, keep in mind, that's 705 billion times the age of the universe to wait for these things to come back. We're not going to have any freaking alignments, okay? So let's just put it that way. Just put that to rest. We're not having any more alignments. Okay. Oh, the alignment. I just saw something on Facebook. There's energy. We have a full moon. Once the full moon is in Aquarius or something, so there's going to be an energy shift. Because why? I don't know. But I get really irritated sometimes when I'm looking at Facebook. Okay.
Horoscope people are going to have some trouble with that.
They are. Okay, so this is a question that came out from an honors physics class. They were talking about gravitation, and somebody asked, what if the sun disappears? And so the teacher in the class said, wait, I'm going to get Dr. Scott in on this, so I'll get him to answer this question. Luckily, she gave me like a day to do some calculations or something. This is not the sun blows up, because there'll still be mass left in the solar system. It's not the sun goes nova. This is, whoop, yoink, the sun's gone. Completely disappears. No mass left in that spot. There's just a pop noise. You can't hear noise in space. But there's just that, boom, gone. Okay. So, all the planets are in elliptical orbits. We get the sun as the focus. Close planets are closer, are faster. The farther planets are slower. Gravitational attraction keeps those planets from, they can't escape. They've got enough energy to go around the sun, but they can't fall in. So if they were in circular orbit, it'd be a nice constant speed. They're not in circular orbit, they're in elliptical, but so the speed varies a little bit here and there. But what if it completely disappeared? Okay, it can't happen. The movie The Core is a terrific, it's a fun popcorn movie. This was maybe a decade ago. What if the core of the Earth stopped spinning? It's a fun popcorn movie. It's got terrible science in it, all the way through. I mean, I have 130 times where I can stop that movie and comment on what's wrong with this movie at this point in time. But I love watching the movie. It's a fun, you got 2 Academy Award winners, not for this movie, but 2 Academy Award winners are in there. It's a fun movie. But their big thing is what if? But what if it could? What if we could? That's the whole reason you make the movies. What if we could? So it can't happen. We can't get rid of the sun. Okay. But, and it's not the same as the nova, we don't want it, we just want yoink, somebody steals the sun and it's gone. What happens if that, what happens then? Well, first of all, it takes 8.3 light minutes for us to know that. 8.3 minutes for that information to get to us, and oh, by the way, there's no sun anymore. If we're on the day side, okay, the sun just went out. What about the night side? The night side's in the night, right? They're not Twitter. Maybe they'll know by Twitter. Somebody will post it on Facebook and say the sun just disappeared or something. Because that would be essentially instantaneous around the Earth as opposed to the 8 minutes.
The moon would go out.
The moon would go out. So if it's a full moon, what if it's a new moon? Aha, I got you there. So it's a new moon. Okay, so what about the loss of gravitational attraction? If the sun's not holding us in orbit anymore. But if we calculate where we are, what's our acceleration of the Earth at that point in space? It's 0.0059. This is, I mean, an elevator ride's got more acceleration. I don't think we would know. It's not like we go, whoa, what just happened? I think the sun, you know, I don't think we're going to feel it. Now, we're going to have a problem with like heat, you know, the warmth of the sun, the radiation is kind of nice for us. But I think we're not going to feel it happening. Okay, well, what happens at that point? What do the planets do? Well, they're just going to go off in tangential lines. Right? They take away that force that's pulling them into the circular-ish orbit, the elliptical orbit, they just go off in a straight line in space. Constant speed, basically whatever they had at that moment in time, that's where they're shooting off. And a fixed direction. Now, let's ignore the interplanet gravitational forces, just because that's going to be really hella messy if I have to deal with that. So, at first I thought, no problem. Right? They just go off in straight lines, everybody's going off in their own straight line, we're good to go. But then I remembered, oh wait, we're faster than the outer planets. We're going to catch up to those outer planets. And then I thought, oh wait, we're slower than the inner planets. They're going to catch up to us. So now it depends on where everybody is when you take the sun away. Because then we could be in trouble. And oh wait, we got an asteroid belt out there. That's essentially the plane of our solar system. And we're the plane, we defined our plane. I don't know why we were crazy enough to define the plane of the solar system of where we were, but that's where the asteroid belt is too. Sort of. Okay, so let's look at today. Here's where the planets are today. And it looks like we're okay. So we are, here's Mercury, Venus, Earth. There's Earth here. And it looks like we're going to shoot off that way. But if I shoot off that way, I got planets going there. I got planets. I think we're good. We're going pretty fast compared to those outer planets. I'm not worried about the outer planets. I am somewhat worried about Mercury. Because Mercury is there aiming sort of toward us. Now, if you think about it though, we're moving out here. Mercury's heading where we were, so we probably could escape Mercury if it happened right now today. But maybe if it happened in a couple of days. So I said, let me run the calculation, and I'll take away the sun. And the first time I did it, and I showed it to the class, and they said, oh look, so we get a near miss of like 4 astronomical units away, that's where Mercury would pass or something. And the student said, Venus, if it's 8 minutes to here, Jupiter is not going to know that the sun's gone, so Jupiter's still going to feel the pull, or acting as though there's a pull, and the outer planets are going to go, oh, I didn't worry about the light time. Even after telling them, look how far away we are, it's 8 minutes until, and Twitter won't find out the others. I use the same joke. And even after telling them that, I forgot to account for the light time myself. It's like, oh crap. So this time when I did it, I made sure that I accounted for the time it takes the light to get out to that planet before I started on its straight line path. Okay. So, how do we figure out if they're going to collide? I've got my x, y, z locations of the planets. I can work out the x, vx, vy, vz. I can work out my three-dimensional velocity. I can work out my three-dimensional position. And I'll show you in a second how I do that in terms of the calculations I use to do that for the theoretical planets. What we don't want to know is where do the two lines cross, because we need the planets to be at that crossing point. I could have a planet go by and another planet go by later. Who cares if they cross that, right? So we need to do it in time. We have to figure out where in time are they close to each other. That's more complicated. Okay. Scary math coming, don't worry about it. First of all, this is a simple kinematics. So Jeff's going to be doing this you've done general physics already, so you've done this, I think. Or Jeff's heading into this. So here's a preview for your next equation. Okay. Here's position, x, y, z. I, j, k are just the vectors. Here's velocity. So here's position plus time times velocity. This is just a simple vector saying I'm starting here and I'm aiming that way because of my velocity. So I've got two vectors, one for each planet. Here's the two lines. What I'm looking for is this time when they are the closest to each other. Not when the two lines cross, they may never cross, but I want to know when am I closest, those two planets are close to each other. So what we have to do is play around with some vector math. Well, we're going to cheat a little bit. So here is my difference between those two vector equations. It's still a vector though. I don't want to deal with a vector. So instead what I'm going to do is say, well, let's make a bigger vector. Or let's double this vector, let's multiply it by itself. Well, vectors are nice because they're directions. It's this much east and that much north and so forth. But if I dot product it, if I square it with itself, I can get it to be a scalar, a number. So now whatever this answer is going to be is just going to be positions and velocities and times, and there's no weird directions in there. Because how do you take a derivative of a direction? That's much harder to do. So I've got my two vectors that I dot product, I square them, I get this big equation. It gets even worse. I want to solve for the time. I want to time when this is the closest it can be. So what I'm going to do is say, take that dot product thing, take a derivative with time. See how that changes with time. When is that 0? That's going to be a minimum, or it's going to be a maximum. Well, luckily the maximum for these are infinity, right? These two planets are way far apart from each other, so it's really going to naturally find a local minimum in time. So scary, 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 blue curve. This is fine, because all this is x's and velocities in the x direction, and y's and velocities in y's. It's just a mishmash of positions and velocities. Well, I've got those for the planets. I can easily get an x, y, z for the planet, and a vx, vy, vz. So I just plug it into this equation here. I got to check to see that the bottom's not 0. That would be bad. You want to divide by 0, you get an infinite. That's no good. As long as the bottom's not 0, then I check to see, do I have a positive time or a negative time? Positive time means it's in the future. It's after this moment whenever I started this. Negative means in the past, who cares? Because if you think about it, it doesn't even work if I go negative time, because I'm saying now is when they all start straight constant velocity. Well, before that in negative time, they weren't straight velocity, right? They were on the curve and gravity's pulling on them, it doesn't count. So I only care about positive. Even if the sun disappeared sometime today, we don't have to worry about it. We're, for all time forward from this moment, we're good, and actually up for 3 weeks from now, we're good for more than 1,000 times the distance between the two planets, we're good. So, okay, we've got some close approaches in there, and there's one where Earth, so remember that Mercury and Earth. Mercury's sort of aiming toward Earth. So if the sun does disappear on the 31st of this month, then we're about 0.07 AUs, astronomical units, away from Mercury at some point in time. And that would be this many days forward. So we're looking at, I get it on the next slide. Whatever 58 days is from the 31st of August. So, but what about that? So, dun dun dun, is that bad? I mean, 0.07 AUs doesn't sound good. It's a number smaller than 1. But AU is the distance from the Earth to the Sun. So that's a pretty big distance. Okay. So here's what, if you look at these two curves, here's what Mercury is going to do, go out in space. Here's what the Earth's going to do. That little tiny line in there, that's how close we're going to get, at least on this scale. But notice the scale. That's 1 astronomical unit. That's 2 astronomical units. That's pretty big, according to the astronomical unit scale.
So, do you have gravitational attraction in here or not?
No. So hang on. Hang on. So, but here's where Mercury's aiming, here's where the Earth is aiming, so here's those two lines that go out and we get, okay. But what about that 0.07? That's 32 times the distance of the Moon. I think we're good, right? Here's the Moon, 32 times farther out from that, that's where Mercury's going to be, and Mercury's a tiny little planet. I think we're fine here. So, whew, again, even though that's a semi-close approach, I think we're good. Okay. Why hardly any collisions? So here's a big giant data chart, but I want to look at the tilts, the orbit tilts. Everybody's got a slightly different tilt than us. You know, here's our 0 because we define the solar system. Everybody else is slightly tilted. So then I said, well, how far do you have to go outward from your current location to change by 1 diameter or 1 radius? Because once you change by a radius, you're now off the plane, right? We're staying in the plane, and they're all going to be jumping off the plane or going below the plane. Well, look how far. They're going hardly any distance, and they're off the plane. So that helps for us. We're basically, everybody's getting out of our way. They're all angled relative to us. They're moving away from the plane, so that's going to save us. Also, to quote the Hobbit, we're quite a little fellow in a wide, wide world. Okay, but what else is out there other than planets? We got that asteroid belt. But my understanding is we don't have a whole lot of mass out there. Got a lot of little things, but there's not a lot of mass. And half of the total mass is in the 4 biggest chunks out there. And they're pretty far apart. Some of the angles are super high. They're 30 degrees off the plane, so they're gone. Wherever they are, they're gone out of here. And the diameter of the Earth, the average distance is 800,000 kilometers between things, big enough things. and we're only 12,000 kilometers, so I think we can sneak by. If Siri's in there, we're going to have some trouble, but, okay. But won't they attract each other? My brother came in from the West Coast when I was doing this calculation originally, and he said, well, if there's no sun, aren't they going to be bound by the gravitational pull of each other? It's like, oh, man, why do I talk to my brother? I was right in the middle, I was just about done, and I didn't want to deal with it. And the center mass is moving, too. So this is the old calculation of where the center mass of the solar system would be without the sun. Here's Jupiter, scaled roughly by sizes, by masses of the planets. So yes, the center of mass of the whole system is now over near Jupiter, and that's going to be a crazy moving system because however they're going off in their angles, the center mass is going to be trying to follow the majority of where the mass is. But then I thought, okay, well, I'm not going to easily be able to deal with, let's have all these be independent objects and they have a gravitational pull, and I'm going to try and keep track of where they are. So I said, let me try it another way, because we want to do it, I wanted to do this with my Physics 1 class. So Physics 1's got kinetic energy, potential energy, and they were just doing the gravity potential energy. So we know the Earth is bound to the sun because it's got more trapped gravitational potential energy than it does kinetic. It's got a certain amount of kinetic, but overall it's trapped. You add up the negative gravity potential, the positive kinetic, you have a negative answer. That means we're trapped. Well, how much gravitational potential energy is there right now without the sun? How much kinetic energy is there? That'll tell me if they're going to be able to escape from each other. So if we do the numbers, I have to add up my gravitational potential energy. Here's our gravitational force is gmm over r squared. Potential, take out one of the r's, gmm over the distance. I've got to throw an extra 1/2 in here because I'm double counting. I'm counting planet 1, planet 2, planet 2, planet 1. So throw in the extra 1/2, but that's how I calculate my total gravitational potential energy. I really should throw a minus sign in here. So that's negative. Kinetic energy, 1/2 mv squared. So every object, how much mass, what's its velocity, 1/2 mv squared, add them all up. That's easy. If the kinetic's more than the potential magnitude, great, we can escape. We have total positive energy in the solar system. If it's less, we can't escape, and then I have to say, oh yeah, my calculation's a bunch of crap because it doesn't count for, well, wait, drum roll, ready? So we have 10 to the 31 in negative potential, 10 to the 35 in kinetic. We're getting out of our way so easily, the planet's just going to be screaming out of the solar system. We're not drawn back in. We've got far less gravitational energy without the sun, which again, you can't get rid of the sun. But without the sun, we're out of here. We've got a factor of 10 to the 4, so 10,000 times more kinetic energy than we need to escape. All we need is exactly this much to escape. We've got 10,000 times more energy than we need. So we're gone. So I think it's reasonable, because I don't want to do the heavy math, it's reasonable to not worry about the gravitational pulls of all the planets relative to each other. And I'm not even dealing with the asteroids. So it's reasonable. So hopefully the takeaway is if the sun does disappear, as in gone, we'll be fine.
No, we won't.
Oh wait,
For other reasons.
we won't collide with anybody. There's a whole bunch of others. So the other thing is, what about the cooling process? How long can we move underground long enough? Because we've got nice heat underground, right? You go far enough down, you get enough heat. Can we move underground far enough? Would we be able to hold on to the atmosphere? So we've got some of the atmosphere, some of the heating and cooling and so forth, but if we're zipping out through space and everything, and then if we keep the atmosphere and it gets really super cold, will we be able to breathe that atmosphere? And can we take it inside underground and then heat it up again to be able to breathe it? So there's a whole host of other issues. All I'm saying is we're not going to collide with anybody. Okay, so at least we've got that comfort. In the cold, cold universe, we're not going to collide with anybody. Okay. When I was done with all this, I realized that if you've got to deal with that gravity potential, the velocities aren't constant anymore. So yes, we have enough energy to escape, but now I can't deal with, wait, we're going to collide on the way out. So I know we can escape the solar system, but we may be colliding, so I'm hoping we don't. Well, we can't lose the sun anyway, so, okay. Math is hard, y'all. It's not. Okay, so heavens above is where I can get some of the night sky stuff that get great satellite predictions. This is the guy that I got for all my astronomical algorithm sort of stuff. And it's Morsels 3, Morsels 4, Morsels 5. He's up to at least 6 or something. So he is the bee's knees, as they used to say. There's my website, but the video for this goes out through the WASP, right through the email. So And I've got more stuff. I've got the moon orbit around the sun if you want that. So if you're not sick of me, I can come back and do more little bits and pieces. So I think that's
Good night and good luck.
okay. Gary, do you have paper? I
We
forgot to
have
ask.
time for 2 questions.
Okay, so questions. Somebody's got to write this down because I got great questions last time. I'm not, no pressure. I'm just saying there were things I had to remember to calculate. Yes, sir.
Did you do this calculation only for a certain day when the sun goes out? or-
Correct. Well, I did it for today and then plus 3 weeks. So I looked from now for 3 weeks. So we got a 3-week window where everything's cool.
So, so the sun had better go out within the next 3 weeks.
Within the next 3 weeks, if we collide with somebody, you come talk to me. Because you can be mad at me. If we collide with somebody and the sun goes out starting today or anytime in the next 3 weeks, then I'll admit I was wrong.
So Jupiter is going to dominate things.
Right?
So I think it'd be interesting and simple to
Getting this, Mary? Gravitational pulls from all the other planets on the Earth.
yeah, to try doing some two-body calculations. If we
If
happen
we
to,
can do 2, we can do like 6 or 7.
sure,
Right.
but it's trivial to do it too.
It's trivial
right?
to do it too. What if it's
then
just us
you
and
picked a
Jupiter?
time when the Earth was, a time interval when the Earth was approximately heading toward Jupiter,
Right,
or leading it slightly,
right.
right? And just see, would Jupiter pull us in?
Would
Or not.
it be leaving the solar system faster than us getting caught up in it, right? Because it's going to
Well,
start
the
rising
tilt-
off the solar system. If we catch up to it close enough, then we get dragged with it
And potentially hit it.
and hit it. Right, exactly. So, Mary,
Or
Earth,
become one of
Jupiter.
those moons.
If we go off in a straight line, will we get captured by Jupiter? I'm not doing the moons.
No. Is it possible
Oh.
to become a moon?
Oh, to become a moon.
Could we find a new career
That's
in a new
an
solar
easier. I'm
system?
going to say no to that.
Wonderful.
I'm going to say no. We can't become a moon of Jupiter. Why not?
Oh.
If we can
We're
catch
too
up to
massive.
Jupiter, the problem is we can't go into orbit around Jupiter, right?
Why not?
We need to, unless we have big rocket burns on the back to slow us down. If we go fast enough to get in.
If we hit one of the moons, it could,
Okay, but I already said I'm not dealing with the two stupid moons of Jupiter, so I'm going to say we can't become one if we just ignore the other damn moons.
So we are going too fast by Jupiter to become a moon.
Correct.
Oh, hell.
And if we're too slow, we're going to get dragged in and hit Jupiter. So, but we're safe, Gary. We don't have to worry about being a moon of Jupiter.
For 3 weeks.
For 3 weeks. We got a 3-week window.
After that, we're.
So after that, you're on your own in terms
Jupiter-
of long-term plans.
But Jupiter is also
How about
moving.
you?
Jupiter's also moving. So my thing is, my argument near the end here is they're all aimed off the solar system.
Right,
plane.
that's,
So as long as Jupiter can skedaddle out of the way, we're going to pass, and we're not going to. It's not going to be an issue. But
could we
Jupiter's
get
much
pulled
slower than
behind
we are.
Jupiter?
What's that?
Could we get towed by Jupiter?
That's it. So Jupiter's much slower than we are.
Okay.
We're going much faster. So can we catch up fast enough before Jupiter leaves the plane? That's the question.
So I think that was about 5 questions
Yeah,
in one
okay.
question. One more quick question.
well, so,
By somebody else.
it could be that this year Jupiter happens to be well out of the ecliptic plane,
Right.
where even if we're aiming out toward it, we'd miss it. But every half of Jupiter's year,
Right.
it's in the ecliptic plane where we could hit it.
Well, no, but okay. No, careful because its orbit's tilted.
Yes.
So the best we could hope for is, I mean, the best in terms of if we want to hit Jupiter, is if it's highest above the plane or lowest below the plane, it's going parallel to the plane. Right? Otherwise, it's going out this way, out that way, down that way, down that way, down that way.
Yeah,
So
but
it's
if it's
tilted.
going
But it
down,
crosses our
approaching
plane.
the plane.
Oh, I see.
Just
It's
when
approaching.
we're
We're
points.
heading toward it. Okay, right. Okay. So, Mary, I'm going to need more computers because contact NSA. See if they're there. Okay.
They don't need them anymore anyway.
That's right. Yeah. Okay. If it's just Earth and Jupiter, I can play it up.
I teach astronomy too.
There you go. Okay.
All
Okay.
right.
Thank you very much. I appreciate
It was
it.
good to see you all tonight.
Yeah, see you.